Welcome to lecture 8 of the NITheCS SATACS course on category theory. Last time we spoke of the concept of an initial object, and we demonstrated its importance by looking at a couple of examples. Firstly, we observed that product of objects in a category, which, as we already know, is an abstraction of multiplication of numbers, can be viewed as an initial object. This would be the same as we did with sum. So sum can be viewed as an initial object, and then product can be viewed as the dual concept to that, which is terminal object. But then we also saw that the natural number system itself can be presented as an initial object in a suitable category. And what I want to show you today is a catalog of examples of things that can be presented as an initial object in a suitable category. And when we do this, we call the property of something being an initial in a suitable category, we call it a universal property. So these things can be defined by universal properties. One thing we mentioned at the last lecture, but we didn't have time to complete talking about it, even start talking about it, was the complex numbers, and let's begin with that. If you recall, our goal with the natural number system was to set up a category where objects represent counting systems in a very abstract sense. So the point of natural number system is that it's a tool for counting things, and then we write down what are the minimal structural ingredients our counting system should have, and we need to have a set of figures and a successor map, the one that tells us which number comes next, and a special number, the one that starts counting. And then it turns out that I don't need to do anything more. I just take then the category of such triples. So I just look at the structural part of the object I'm trying to define. I take the category of these structures. I define morphisms in a suitable way by essentially preserving the structure that I've identified. And then I take initial object in that category, and it turns out to give me exactly the thing I was after. So the property of initiality, magically gives me the desired property of the structure we are after. So maybe I should pause here a little bit and say that a mathematical structure always has two components. Which is the structure itself and the properties it needs to satisfy. So structure and properties. Another way of thinking about this is language and axioms. So a logician would think of it this way. A mathematical theory in the sense of logic, mathematical logic, would be a coupling of two things, of the language, which describes what kind of constructions can be performed in this theory, And then the axioms that tells us what are the assumptions we assume to be true. So what are the assumptions we believe to be true about our theory? Here is an example of this breakdown. If I take, for instance, definition of a group. A group is a set G equipped with a binary operation, right? And then there is also inverses and the identity element. We can also put that as part of the structure, or we could have kept it as part of the properties. So sometimes there are many ways of presenting the same thing. So this would be the structure, and the properties would be the axioms saying we want the multiplication to be associative, and we want the inverses to behave like inverses, and we also want the identity element to behave in a suitable way. By the way, you can chop off some of these axioms. I don't remember now, it is this pair or this pair, and derive them from the others. Anyway, so what happens now is that if we go back to this list, so to define each of these things are mathematical structures of their own kind, and to define them, what we will take is we will take all possible structures without, so we disregard the properties, we just focus on structures. We take the category of these structures, and then the properties we were after will turn out to define exactly an initial object in this category. So for the natural number system, this was the structural part, and we never stated the properties. They are the Peano-Dedekind axioms, but it turns out that they're equivalent to the natural number system being initial in the category of these structures which we call counting systems. So let's follow now this idea and try to describe the complex number system as an initial object in a suitable category of structures. So what is a complex number system? Well, by the way, coincidentally, this links to Galois theory, right? So there are certain equations you can solve in the real number system, certain polynomial equations you can solve there, but certain ones you can't solve. And specifically, if I take the real number system, I do not have an element in the real number system that satisfies the equation x squared equals -1. So I could write this by saying that x squared plus 1 equals 0 doesn't have a solution. So then the idea of the complex number system is to have an extension of the real number system. So let's represent it by a mapping. So this is our familiar real number system. This is what we want to be the complex number system. It is an extension in the sense that it is a field. So I'm now describing the structural part of my definition of complex number system. It is a field, and it is equipped with, so maybe because at this point it's an abstract field, so let me just call it F. It's a field F. It's equipped with a map. Let me call it I. No, maybe I shouldn't call it I, because I will be the element whose square is not -1. It's equipped with a map. Let me call it E. From the reals, and in fact to F, and in fact I want this to be a field homomorphism. So this is a field. This is a field homomorphism. And there is a third ingredient I want in my structure. I want a specific number, specific element of the field F, such that x squared plus 1 is 0. So this is where we'll stop describing the structural part of complex numbers. It's kind of similar to the natural number system, right? Because we had a set, we had a function, we had an element. And here we have similar data, except that now these are not sets anymore. They're more than that. So this is a field. It's a map from real numbers to that field, which is a field homomorphism. By the way, a field is a structure that has addition and multiplication that behave the usual way that we expect. And there is a distinguished element in F whose square is -1. So in a sense, this is a wish list, right? We want complex numbers to be something like this. But then it turns out that there are many different solutions to this triple. So you can find many different fields F that come with such a map field homomorphism and come with a special element like that. So we form the category of these things, and then we take the initial object there. And then it turns out that we will get complex numbers. So the triple C, the map E, which maps a real number R to itself, and the element I, the one we know, the complex number I, which is an element of C. This is an initial object in the category of triples of the above form.
So can we say here is like initial object is in some sense the smallest?
If my category is a preorder, so if for any two objects there is always at most one morphism between them, so then I can think of it in terms of binary relation. We usually call it less or equal. Then in this case, in an ordered set, more specifically in an ordered set, the initial object will be exactly the smallest element. But otherwise, the word smallest is a bit dangerous because you can have smaller things which are degenerate in some sense. For instance, if you take the category of rings, right, with identity, the initial object there, okay, let's look at another example. In the category of rings with identity, so these are triples, R plus dot 1 and 0. And of course, we also have additive inverses, so it's minus 1, minus operation is also there. And then the usual axioms hold that say that additional multiplication behave nicely with each other, except that in a ring, unlike in a field, we don't have multiplicative inverses of non-zero elements. In this category, an initial object is given by guess what? What do you think will be an initial object? Sorry?
Whole numbers?
Yes, integers. That's right. With the usual operations. And so this is not smallest string, right? Because you can have Z3, Z modulo 3 and modulo 2, that they're smaller in some sense. But it's initial.
Yeah, that's true.
So the initial object can be big. In a sense, the initial object is smallest it is smallest in a suitable sense. So when you have, let me show you this pictorial analogy. When we have a structure, there can the two things can happen to a structure. There could be a larger structure that contains it, right? So think of S being embedded into some S prime. But there can also be a structure that has been obtained from S by gluing things. So a projection. An initial object usually will be such that S prime doesn't exist. So it's minimal in the sense that it doesn't have extra bits. It doesn't have extra things that are unnecessary, kind of. But at the same time, so in that sense, it's smallest, but at the same time, it's largest in the sense that it doesn't glue anything inside that minimal component. By gluing, I mean, we could have, like, integers modulo 5 is, for instance, can be obtained from integers by gluing some numbers with each other, right? So it doesn't do that. So there are these two senses in which something can be small or large. So in this sense, it's the largest. The initial object is the largest in this sense, but in that sense, it is the smallest.
It's
And by the way, yeah, sorry.
I was just going to say it's fascinating that the kind of first example of a ring we encounter happens to be the initial one.
Well, if you think about it, how did we come up with the axioms of a ring? They come from integers, right? So now we want the integers to be a place where we can add things in an associative way, in a commutative way, and multiply things in a distributive way, and so on. We want all of these, and then it's kind of, by the philosophy of category theory, it's kind of natural that the initial object will end up being integers, because that's what we were after in a sense. Does that make sense?
It does. It's just interesting, right? Because there are situations where we don't, where the first example of something we encounter isn't particularly special. But I suppose, as you say here, it's almost constructed to be special.
You could take the ring where 0 equals 1. That will be actually the terminal object. But yeah, sure. Since we mentioned this idea of gluing, now I also want to look at that. So as a separate example, but maybe I'm going too fast. So let's first go back a little bit and kind of confirm our ideas about this. So where are we here? So let's try to sketch a proof of why will this be the case? Why will the complex number system be initial among all such things? So we want to construct a unique homomorphism. I didn't describe what morphisms are, but it's kind of natural what they should be, right? So they should be field homomorphisms. And of course, every field homomorphism is injective. And so that's why Alexander was thinking it should be smallest, because you never have these kinds of things in that category. So there should be a field homomorphism from C to F, and a unique one, right? Such that sending, which kind of is doesn't change the real numbers. So real numbers live both in F and in C, right? And so if I take f of r, where r is a real number viewed as a complex number, that should be exactly the same as e of f of r. So sorry, it should be exactly what? It should be exactly e of r. Maybe it's useful to draw a commutative triangle here. So we've got real numbers, and our objects, our structures are field F together with this homomorphism E and a special element X. And as before, we can also always describe a special element as morphism from the singleton set, which itself is a terminal object in the category of sets. So we can think of it like that. So our structure, and of course, X is a special element in the sense that it's squared equals -1. Our structure consists of data of these things. Now, another structure would be of this kind. So I mean, F is this another structure, but C itself is also a structure of this kind. And so we can draw it in here as well. So this mapping is the one that chooses number I, and this is the usual inclusion of reals into complex numbers. And in fact, I can even think of this as almost resembling the sum diagram we had, right? The way we defined sum, except that now we changed what our mappings are, these inclusions. So I can redraw this in this way, right? So this is the inclusion, and this is I, and here we have F, and here we have E, and here we have what is this, X. And now we want to prove that there is a unique field homomorphism making these triangles commutative. So unique, I'm claiming there is a unique H of that kind. So first I will probably try to show that it exists, right? How will I define H on a complex number? Well, a complex number has the form A plus BI, right? And because H must be a homomorphism, this must equal H of A plus H of BI. But I can now do more than that. A is a real number, right? So it comes from here. So H of that must be the same as E of that. So this will be E of A plus, and H also must preserve multiplication. So it will be H of B times H of I. But then, let me move it to the center. But then, what about H of B? Well, H of B, again, B is a real number, right? So H of B, so B comes from here. B goes to B here, and by H it will be the same as E of B. So this must be E of B times H of I. But what is H of I? It's star is being met by I and then H. So it will be X of star, which is X. So you see, this actually proves that there is at most one H, because if I have such H, then it must equal, H of each complex number must equal this, right? So this proves there is at most one H. How do we prove that it actually does exist? Well, now that we know that it has to be defined this way, we can define it this way, but we just have to check that it's a field homomorphism. So if I define H this way, will it be a field homomorphism? It turns out it's very easy to check that it will be. Any questions on this one before we move on to the next proof?
So may I ask a question?
Yes.
About what type of morphism B here says that there's only one of them?
About what type of morphism, sorry?
Yeah, so we are saying that there's at most one morphism of some type, and I'm not sure about what type of morphisms we are talking about. Like, if I'm not mistaken, the degree of extension of complex numbers is 2. So yeah, I'm a bit confused here.
So such that F is a field homomorphism?
Yeah.
and the triangles commute. So H composed with this inclusion thing equals E, and H composed with I equals X. This is how we define morphisms between such structures. We never properly defined them, but yeah, that's what we meant.
So we have two maps on right as well, yeah? Oh, okay. Thanks.
Mm-hmm. So our structures are these kinds of things. So here is one. This is the complex number structure. This is a random one. And we're proving that there is a unique morphism between them. And morphisms are defined so that these three properties hold. Kwatisa, are you happy with that? Or you
Yes,
have some questions? Okay, wonderful.
I am happy.
Fantastic. Good morning, Linda. I didn't say hi to you before we started the lecture. How are you doing?
I'm doing quite fine. How are you?
Good, thanks. Are you also happy with this, or you want to ask some question about this?
No, I'm fine.
Okay. Okay, so we now kind of partially convinced ourselves that this is true. Now let's look at the category of rings with identity. Let's look at this situation. So why will there be exactly one? Of course, here we're looking for ring homomorphisms, right? H, which preserves addition, preserves multiplication, preserves the special element 1, preserves 0, and then it also preserves minuses. But the thing is that because plus is an abelian group and the minus is inverses, it will automatically be preserved. It's a result about homomorphism of abelian groups. It's sufficient to preserve just plus, and you automatically get your minus and 0 preserved. Because of that, you might also want to define a ring just as this structure without mentioning 0 and minus 1, because they automatically get preserved. Anyhow, so let's prove that there is exactly one ring, such a ring homomorphism. I mean, this is called a ring homomorphism, what I described. So let's prove there is exactly one from integers to any other ring. So once again, we take H and we are trying to evaluate it at some element Z, at some integer Z. And let's also, in this case, like before, prove that there is at most one, and then they will get a formula that will also give us that it must exist after we check it's a ring homomorphism. So what is H of Z equal? What it must be equal according to the restrictions we have on H? Well, Z itself is 1 plus 1 Z many times, right? So Z is an integer. If of course Z is positive, so let's maybe we first consider case 1 when Z is bigger or equal to 0. Then I can write Z as 1 plus 1 Z many times. And now I can use induction here. One by one, I can separate the plus 1. So because H preserves addition, this will be the same as H of 1 plus 1 Z minus 1 many times plus H of 1. And then I can continue doing this, and eventually I will get H of 1 plus H of 1 Z many times. Maybe I'll just write Z like before. But H of 1 is forced to be something as well, right? Maybe I should use primes to represent the structure of the random ring here. So I'll put a prime here and here as well. H of 1 must be 1 prime, right? So we'll get this. And now we see that at least for positive or non-negative integers, there is H of Z is forced to be equal to this object, which is a specific object, right? It's a specific object in R. It's the one obtained by taking the 1 prime and adding to itself z many times. So that does show that h is at most 1, at least up to its definition on positive numbers. But of course, with negative numbers, it will be similar, because now we can rewrite, if in case 2, we can be dealt like this. So case 2, h of minus z, so where z is still, so let me call it minus t. So z equals minus t, where t now is bigger or equal to 0. So that's case 2. H of minus t is going to be the same, must be the same as minus prime h of t, by the fact that minus must also be preserved. And then we again arrive to something that's forced, right? Because now we can use the previous result to say that, okay, this must be the same as 1 prime plus 1 prime all the way like that, t many times. So again, we arrive to a unique value for this. And then the next, so this shows that there is at most 1 h, and then the next step is to define h this way and prove that it actually is a ring homomorphism. And that's not a difficult exercise. In each of these proofs, we're of course using our knowledge and construction of this object, right? Here it was integers, and in the other case, we used our knowledge of complex numbers. We used the fact that complex numbers can be represented this way. And by the way, the fact that this is well defined, this h here, also, I mean, I should have underlined this, also uses the fact that complex numbers can be represented this way in a unique way. So the pair A, B is unique for each complex number. Anyhow, so now I want to look at another example where we take a quotient. It could be of a structure or of a set. Let's look at a topological scenario. So, for instance, let's look at Z12. Let's try to define Z12 as by a universal property. So what is Z12? Well, Z12 is our clock, right? 13 is the same as 1. That's basically what it is. So that will be our structure. So as structure, consider things. These things should be groups, or maybe even rings. I'll just work with group for now. That inserts all of the integers in it. So there is some insertion here. Let's call it E again. There's an E from Z to G. And furthermore, we want in G okay, let this be rings for simplicity's sake. So G is a ring, and this must be a ring homomorphism. And of course, because it's a ring homomorphism, 1 will be mapped to the identity here. And now we want 1 plus 1, 13 many times to equal to 1. So it's an extra requirement we put. It's no longer an element that we pick from G, but just an extra requirement we put on G. So our diagram will now look like this. We're considering all possible ring homomorphisms going out of Z to some ring R, let's say. And we're looking for initial such. So if I have 2 of them, so the only thing I know about R is that, apart from the fact that I'm given this ring homomorphism, I also know that 13 times, or rather 1 plus 1, 13 times equals 1. That's all I know about R. And if I have two such, so if I have another ring with a homomorphism into it from integers, such that 1 plus 1, so these are, let's think of them as inclusions, such that 1 plus 1 13 times gives me 1. A homomorphism between them, H, is just a ring homomorphism that makes this triangle commutative. So let's try to prove now that Z12 is the initial object here. First, we must prove, well, I guess we'll probably do the same, prove that there is at most one H first. So I'll take H. Now, every element from Z12 comes from Z, right? And this is not quite inclusion. It wasn't correct to call it inclusion, right? It's because in this, it won't be inclusion. It will be a projection, actually. So let's keep calling it E. And this will be E, and this will be some E prime. So then my formula should rather be E of 1 plus E of 1 13 times must equal E of 1. And here it should be E prime of 1 plus prime E prime of 1 must be equal to E prime of 1. Okay, so everything here comes from an integer, right? And because of that, so if I take H of random x, there will be some integer such that x equals E of that integer. And then this will, because of commutativity of triangle, this will have to equal E prime of that integer. So this does prove that there is at most one H. How do we know there exists one? Well, we can use this to define it that way, right? But the problem, of course, is that for each x, there might be many different zx's. So if I now say that we define h of x to be E prime of zx, so define it this way. The first question I need to ask myself is whether it's well defined, whether the choice of the zx matters. And then it turns out that because S satisfies this rule, it won't matter. So I'll just demonstrate it on an example. So let's say I'm now working with H of 2. Well, in our case, we could have actually used a specific representation of Z12. I can really think of this as number 0, or maybe for the sake of the clock, 1, 2, and all the way to 12. I can really think of it like that. Yes. And then I can just say define H of x to be, so basically I can take Zx to equal x, because they're the same numbers that we encounter here. So I can just define H of x to equal E prime of x. And then we need to check that H, so it will automatically, yeah, so we have to check that H is a homomorphism, is a ring homomorphism. But we also need to check that this commutes. H of E of Z always equals E prime of Z. By the way, we never said what this E is in our case, right? E of Z is just Z modulo 12 plus 1, because we are starting here from 1 instead of 0. Is this fine? It was also a bit sketchy. Mhm. So this is just to give you an idea of how to kind of behave in situations like this. So you see a common pattern, right? Every time you will have to physically check that something is indeed an initial object, you will have to first see what restrictions are forcing H to how they're forcing H to behave, and then that restriction will also give you an idea how to define H. Let's look at two more examples of this. A vector space of dimension n. So that can also be presented as an initial object. A vector space of dimension n. So what do we want from a vector space of dimension n? Well, we want, first of all, it to be a vector space V. And then we want to have n linearly independent vectors in it, right? But we could think of these vectors being linearly independent be something that should come out as a consequence of being initial. So as our structures, let's just take pairs V with a system. So let me write it as a mapping with a mapping of numbers from 1 to n into it. So every number I is mapped to V of I, which we write as V subscript I. So these are our objects of the category. So they are pairs, basically. So a vector space of dimension n is going to be an initial object in the category of pairs. V and small v, where small v is a function from 1 to n, from the set of numbers from 1 to n, to big V, where V is a vector space. You see, the structural part here is very mild. We just have a random function. It could be selecting all of these, all of the VI vectors could be the zero vector. So it doesn't have to give me an n-dimensional space yet, but the initial object will be. So let's look at that. So these are my objects, and if I have another one, of course, a homomorphism will be, a morphism between these will be a linear map here, such that H composed with V equals W. In other words, H of each VI equals WI. And then now it turns out that here, if I put here n-dimensional vector space, it will be initial object. And let's prove that. And let's use a specific n-dimensional vector space, namely R to the n, where our VI is defined in a specific way. So VI is the vector where I'm going to use columns for writing vectors in Rn, where everywhere we've got zeros except the ith position where it's 1. So this is the ith position. So this is the standard basis of the vector space Rn, right? So let's prove that H exists and is unique. In the same way, we will first force it to be unique. So what is H of a random vector x1 up to xn? Okay, maybe you can help me here. now from the experience we've already had, what should I do next? How should I expand this to force uniqueness of H? Any ideas? So let me remind you what we're doing here. Objects of our category are things like this. This is one object, this is another one. Where here we have a vector space, and here we just have a map, a function. No requirements on this. A morphism from one object to another is a function, a linear map, in fact, from one space to the other, such that the triangle commutes, such that this composite equals that. Now I'm proving that if I take here n-dimensional vector space, it will be an initial object in such a category. Remember, this part is fixed. To prove that, I will try to see that the fact that H was a linear map and the fact that the triangle is commute, that it forces H to be defined in a unique way. So I take my H and I try to evaluate it at a vector, and now I want to see if it will be forced, some formula on H will be forced on the value of H. So what do you think should be our approach to achieving that?
Sorry, is VI standard basis here, or?
Yeah, this is the standard basis. So the VI is the vector where we have zeros everywhere except the ith position.
Could we write x1 up to xn as a, what is it, a linear span using our standard basis? So x1 times v1 plus.
Yeah, well done. Yes. So we will first expand our x vector this way that you suggest. Thank you very much. And now we use the fact that H is a linear map. A linear map by definition must preserve linear combinations, right? That's one way of defining a linear map. So it preserves all linear combinations, including the empty one, which is we need to preserve zero. Well, if we don't, we can also derive that from the non-empty case, right? Okay, so preserving linear combinations in this case means that it must equal x1 times h of 1, 0, 0, plus all the way xn h of 0, 0, 0, 1. But this is, of course, the same as h of v1, and it goes all the way to h of vn. And h of v1 is forced to be something, right? Because of commutativity of this triangle. You see here, h of v1 is w1. So this will be x1 w1 plus all the way up to xn wn. And now finally we have a forced value. So h of a random vector must be this. That will prove uniqueness of h. What about existence of h? Well, we define h this way. So we'll define h to be given this way. And then we will prove that it is actually a linear map. It's not difficult to do that. I'm skipping those parts, but it's not difficult to do that. And we will also need to prove that the triangle commutes, which is maybe even easier because if I just substitute here zeros everywhere except one value of 1, that will pick out the corresponding term here, which will be the corresponding W term. And hence it will give me this formula. Okay. Can I move to the last example of an initial object? So here in the in this example, with integers, we had slightly different situation than in all the other examples, where the universal object we were building wasn't bigger than this fixed pin. Actually, there was a projection, right? So this last example will also be like that. And this will be a topological example. How can we present the construction of a torus as an initial object? So what is a torus? A torus is a topological space. If you don't know what a topological space is, you can just think of it set theoretically. You can forget about it. Topological structure. It's an object like this. We are looking at the surface only, this example. So if I cut it, it's a donut, right? If I cut it somewhere there, I will get this round cut. So I can actually cut it and open it up, and then I will get a cylinder, right? So imagine if you twist around the cylinder and you attach this onto that, you'll get a torus. Okay, but I can cut a cylinder as well. So there is this first cut I did was around here, right? So on my cylinder, let me mark that here. Actually, I don't want to mark it there. I will now do a second cut. I will cut it here. I will cut the cylinder here and open it up. And this line on the torus, when I connect the two endpoints of the cylinder on the torus, this line will be looking like this, right? So there's two lines, the yellow line and the white. Maybe I'll use a red color for that, and red line. First, we do the red cut. So this creates thing here and thing there. And then we do the yellow cut. And then this way we will get a sheet of paper, possibly, right? So my red cutting edges are now like shown like this here, and the yellow ones will be here and there. Okay, so this cylinder is kind of the intermediate step, but I actually want to now think of it in one go. So I've got my rectangular piece of material, and I can think of making torus out of it as a map. In fact, it will be topologically continuous map. What does this map do? It takes points on the top yellow line. It takes these points to these points here, and the corresponding points on the yellow line on the torus. And it takes the red ones correspondingly here. Now I can abstract away and just look at the structural part, and then initial object will give me exactly the torus. So what is the structural part? So any other such structure will be mapping my rectangular sheet of paper or any material into some topological space T. And at this stage, let's specify the dimensions and coordinates of this. So let's say that this sheet of paper is the interval 0, 2. Well, it more looks like 0, 3, multiplied by the interval 0, 1. So the only requirement I'm going to put on my mapping, so this is the mapping to get the torus. I'm going to call it small t, maybe not small. Yeah, small t, but I'm just going to rename this one. And this is some arbitrary other shape, S, and let me call this small s. So the only requirement we put on S is that S of the red part should match the corresponding points. So this point should match with that. So I'm kind of describing the fact that I want my rectangular piece of paper to be folded in a certain way. So S of coordinates of the form 0y must always equal S of 3y. So here is an example for point 0y, and here is another point 3y. But I also want the yellow parts to match, right? So I also want S of x0, so this will be a random point here, x0, to match with S of x1. So I want the values of S on those points to be the same. So as a category theorist, when I'm building a torus, I can say, let's build a space inside which I will kind of fold my rectangle in that space in such a way that these hold for every x and for every y. So all I'm saying is that when I insert my rectangle inside my space, I want the points here to match with the points here, and I want points here to match with the points there. Now, there are many such ways of doing that. For instance, S could be a singleton set. Like I could squash everything. I could take this sheet of paper and squash everything into just a single point. It will trivially satisfy these equalities. So I've abstracted too much. Just the structural part is too little information. It doesn't give me a torus yet. Such an object will not be a torus. But then I take initial object in the category of such things. So let me define what a morphism is. So if I have another such thing, and it will end up being our torus, then a morphism will be a continuous map such that the triangle commutes. So however rectangle is inserted in this space, then after transforming it by H, I will get exactly the insertion of the rectangle in this other space. And then if these are the morphisms in the corresponding category, the initial object will be exactly the torus. Let's prove that. Well, I think to formally prove that, we will have to have a formal representation of the torus, and that will be a long technical process, so we'll just intuitively do that. Or rather geometrically. So let's pick a random point on the torus. Let's call it something. Let's call it A. I want to see what to do with A. Will the value H of A be forced or not? Well, if I look at this, it matters whether A comes from the yellow bit, the red bit, or none of them, right? So there are three cases, right? When A doesn't belong to the yellow area, when A does belong to the yellow area, so if let's say A is somewhere here, then there are two options where it came from via T. It came from either there or here, right? So H of the A will have to be, so you see, if A comes from yellow area, it means that A itself is equal to T of some value. It equals to T of, let's say, x1, or it equals to T of x0. But then because of commutativity of this triangle, H of that must be S of the corresponding values. And there is a potential danger here, because what if S maps these two values to different places? Then H won't be well defined. But it doesn't, because we require that S also maps them in the same way. So if if A comes from the yellow area, we can just define it to H of A that must be equal by a commutativity triangle of S of let's say XA1, where XA is the x coordinate of that corresponding point in the yellow area on the rectangle. If A comes from the red area, we can write a similar formula. Then it must be S of, let's say, 0, Y, A. Now we have to be careful when setting up this definition of H. I mean, we're also at the same time trying to confirm that H will exist, so it's well defined. So what if it comes both from yellow and red area, right? So what if it's here, for instance? Well, then it will be one of those corner points, right? Here, 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 or here. And then again, by these formulas, we will see that S will have to map them to the same place, so it's no problem. And the third case is when it doesn't come from any of those areas. Then we can just define it to be S of XA, YA, where, because if A doesn't come from any of those areas, then there will be a unique point on the rectangle that maps to A via T. And because it's unique, then I can just map that by S, and I'll be fine. And I have to do that because the triangle, once again, triangle has to commute. So we kind of convinced ourselves that this must be how H must be defined, but at the same time, we also convinced ourselves that if I define H this way, it will be well defined. I still need to prove it's continuous. It's a continuous map. And for that, I will have to use the more rigorous notion of my torus to represent it as a specific mathematical object with its topology, and then prove that H is continuous. It might take a few pages of writing if one does it really, really properly. I mean, there are many ways you can represent a torus. You can represent it inside R-cube using rotational symmetry, or you can represent it as a set theoretic quotient, which is essentially doing this already halfway.
So is like what we are doing here and what we did in another example with Z over 12, when I'm not mistaken, actually talking about universal property of quotient objects.
Yes.
Ah, okay.
That is. So these two are different examples of the same idea of quotient object. In the first case, we did quotient object in the category of rings. And here we're doing quotient object in the category of topological spaces. Okay, so one can go on. Universal properties are universal. It's the amount of things you can represent this way is simply too big. You talked about earlier, Alexander, you told us that you wanted to study some version of Galois theory where you were encountering what was it? Projective
yeah, projective limits.
Projective elements. Oh, okay, that's something slightly different. But there are many constructions in mathematics where so when we build mathematical objects, sometimes the construction is very difficult. I mean, these examples are not so difficult, maybe. Well, maybe torus now is a bit more difficult than the previous ones. We know how to write down construction of integers, for instance, and complex numbers. But the more advanced objects we're dealing with, the more complicated these constructions get. And the nice thing is that because the universal property fully captures the behavior of this object that you've constructed, in most of the cases, you no longer need to use the construction to prove things about the object. You can use the universal property. And the universal property is very simple. It's a very abstract thing, and therefore it's very simple. And so that is the application of universal properties, that you can prove theorems about your very complex mathematical objects by knowing in which sense they're universal, which universal property they satisfy, which is a simple property, as opposed to representing that mathematical object in its very complicated technical and concrete construction, and then using that construction to computationally establish further properties you're interested in. So that's kind of the main idea why we need universal properties and why they're useful. But of course, the construction is also useful, but you only need it to use once. You need to use the construction very often. Sometimes you don't even need to use the construction. There are tools in category theory that avoid you using the construction fully. But in many cases, you do need to use construction to prove that your initial object exists. You need to know that something exists to assume that to derive consequences from its existence, right? So the way it goes is that you prove that your initial object exists. So we prove that complex numbers exist, for instance, by constructing it the usual way as pairs of real numbers. But after we've proven that it exists, in most cases, we no longer need to use its explicit construction. We can just use universal property, which is simpler. So that's the general framework.
So it's like the tensor product being an initial object in the category of vector spaces, if I'm not mistaken.
That's a good one. So there is a suitable way in which we can express tensor product as an initial object as well. Let's maybe briefly mention that as well, since you're familiar with that. So if I have two, let's talk about tensor product of vector spaces. If I have two vector spaces, V and W, their tensor product is an initial object in the following category. So you again have this mapping, insertion of, but this time insertion of the Cartesian product into your tensor product, but this is not a linear map. It's just a map. And then these are the objects of the category. So objects are some vector space U with a map from V cross W to U. Any map. But then the morphisms are not linear maps, but bilinear maps between, sorry, what am I talking about now? I confused myself. No, sorry. I swapped things around. So these are bilinear maps, okay? And these ones will be linear maps. So this is not just any map, it's a bilinear map, which means the following, that HV dash is linear for every V, and H dash W is linear for every W. So we take objects to be a vector space together with a bilinear map from V and W have been fixed in advance. We want to define tensor product of two vector spaces V and W. So V and W are fixed vector spaces. We start with them. And then we say, let's take all possible vector spaces together with a map from V cross W to U, but not just any map, the one that's bilinear. I shouldn't call this H, I should call this something else. Let's call this U, and let's call this, well, actually, let's call this F, and let's call this G. Now, a morphism from one object, from one bilinear map to another bilinear map, is a linear map H, which makes the triangle commutative. And initial object in this category will be exactly what is called tensor product. We can construct the tensor product as follows. You take the free vector space over V cross W. So the basis of your vector space will be pairs of vectors. And then you start quotienting it out by ensuring that F will be bilinear. And you can write down things that need to be quotiented out. So it is a heavy construction. It's an unpleasant thing to do. But I think in mathematics, the only time you really encounter things that are a bit unpleasant is when you have to do lots of, because mathematics by nature is a very abstract field, and when you're working in the abstract environment, that simplifies life and you feel good. But sometimes in mathematics, you have to do concrete things as well. And if it gets too concrete, it might be a bit unpleasant to work with it because it feels like we are back to real life. And so you will have to kind of describe exactly what elements needs to be stuck to each other, what kind of quotient do we want, and then perform this quotient, and then check that you get a vector space and all of that, and eventually you will be proving that your tensor product, the way people classically define it, is an initial object. But as I said before, when you want to use this tensor product for various mathematical theorems, you will, in most cases, unless you're doing some computations inside your vector space, you'll just be using this universal property.
Well, thank you. Yeah, I brought it up as one of those constructions which are kind of rigorous, but once you have it, it's much easier.
Yeah. Okay. Now, I want to now take us back to arithmetic and transform this what we call higher arithmetic, transform it into higher analysis in some sense. This is a bit overstatement. So just like we captured arithmetic only up to level of additional multiplication of whole numbers, actually positive whole numbers, right? We never said how we can define negative objects in a category and so on, that they actually do not exist. You can do some artificial things, but they're not as important and interesting as the natural number case. Now, in the same way, we're going to define a concept from analysis, which is called a limit. But this doesn't capture analysis fully. So analysis after limits defines derivatives. And just like our product and sum of objects in a category do not allow us to work with quotient objects, or I mean, by quotient object, I mean 1 over something, or negative objects. In the same way, this notion of limit we will define in a category will not allow us to work with derivatives. Although there are things called derived functors and derived categories, but there's something's not delivered. So what is a limit in a general category? It will be a generalization of limit from analysis, obviously. And it will be also a generalization of product of objects. So we will be able to see product as a discrete kind of limit, which in analysis doesn't exist. Okay, so let's first represent a usual limit of numbers as an, this time I want terminal objects, so maybe I'll work with, yeah, we'll represent as a terminal object, so the dual of initial object. And then we will see from there how we can extract this and generalize and get a more general notion of a limit. Okay, so let's take what is your favorite limit? Favorite sequence with its limit? What would that be?
Maybe Euler's number and it being a limit of the sum 1/1 plus 1/1 plus 1/2 and so on.
Let's do something simpler, Alexander.
So maybe the very first limit I have encountered in mathematics, I think, geometric progression.
Okay. How is that a limit?
So 1/2 plus 1/4 plus and so on and so forth.
Okay, that's the one. That's the one I was looking for. Thank you. Sorry for not being flexible. So let's take something very simple. Consider the sequence 1/n. So 1/1, 1/2, 1/3, and so on. We have this 1/n, the general terminate goes on. The limit of the sequence obviously is n is 0. And now let's try to represent it as a sort of initial object. So no, I said terminal, right? We can actually do it both because they're doing to each other. But since we've been talking about initial, the thing is that what the other thing will be called colimit, the one that corresponds to initial object. So that's why I'm avoiding to do it that way. Anyhow, so one way we can represent it is, well, first of all, we want to represent, because we'll be considering morphisms between things, right? So we want to represent numbers as maybe sets. And we could take I think I want an increasing sequence. If I want to represent it as a limit, then I want an increasing sequence, otherwise it will be the other way around. No, I don't need an increasing sequence. So let's represent a number x as a set of all numbers. And I'm thinking whether it should be greater or equal to x or less or equal to x. Yeah, of all numbers less or equal to x. I think this is what I want. Okay, then this sequence that I've got, so my sequence minus infinity will become the following. It will minus infinity 1/1. Then we have minus infinity 1/2, and it goes on like that, right? And every next one is contained in the previous one, isn't it? So these numbers are all contained here. So I've got this inclusion of sets. And it's an infinite, it's an infinite set, right? This is constantly decreasing this set. Now, the structure we're going to describe will be a set S that has a map, an inclusion map, into Yeah, actually, it doesn't have to be an inclusion map. It can be an arbitrary map as well. It has these maps into each of these things. It goes on like that. So it's a family of maps: S1, S2, S3, S4. Then here we have nth term Sn, and it goes on like that. Of course, I do want these triangles that are being formed to be commutative. I want going this way to be the same as going this way, and going that way to be the same as going that way, and so on. You might say, okay, if going this way is the same as going that way, then we can just scrap this off. We can recover it from here. Sure, we can keep scrapping these off, but because we never have a last arrow, because it goes on infinitely, we will never be able to reduce so we can we'll have to keep something, and then after that, everything. So it doesn't really make sense to take anything off. So these are the objects of the category. So this diagram below is fixed. And the objects of the category are such, we call them cones over the diagram. So this thing we call a cone. It looks like a cone, right? It looks like a cone, conic shape. So what is a cone? It's a single object with maps going into each of the nodes of my diagram below. And then every triangle that gets formed, I've got this triangle to be commutative. So that's a cone. And now, if I have two different cones, what will be a morphism between them? So let's say I've got another cone T. It will be something like this, right? T1, T2, T3, and then it goes on. So there's at some point there is Tn. So that's another cone. So now we have two cones, cone S and cone T. I should actually say pair SS because the family of those maps is also part of the cone. So you really want to think of this geometrically. So you've got this base diagram, and you've got one cone over it, and then you've got another cone over it. Now, for this other cone to be terminal, what does that mean? That there is a unique morphism from the S cone to the T cone, right? But I haven't described what a morphism is yet. A morphism from S to T, so the H, now we're switching from initial objects to terminal objects, so the direction now swaps around. A morphism is a map H, is a function H, which makes each of these triangles commutative. So basically everything needs to be commutative. So H, so Ti composed with H must equal always Si for every I. For every I from 1 to infinity. Right, let me rather write it like this. And so repeating myself once again, so this composite must equal S1, the next composite must equal S2, that composite must equal S3, and it goes on like that. I think there is no space for S4 here, actually. I shouldn't have drawn that. What will be a terminal object in this category? So which such cone will have the property that for every S cone, there will be unique H fulfilling this requirement. And the answer is, it turns out that the answer is exactly the set that represents number 0 according to our rule. So it will be the set that is for minus infinity to 0. where each of the T maps are the inclusion maps. So in a cone, they didn't have to be inclusion maps. So the S maps do not have to be inclusion maps. Here in this diagram, they are, because the diagram is fixed. Now let's prove that. So let's prove that when I take T to be this, then for every other cone S, I will have exactly one H. I will make my picture slightly smaller to be able to look at it while we write out the proof. There we go. So I now follow the same procedure. I will pick a random element from S. So let's pick an element X, let's say, from S. And now I will try to prove that H of X must be something. It must be forced to be something, no? Okay. What must it be forced to equal? Well, there's something wrong here, right? Sorry, I made a mistake. The terminal object in here will be not number 0, but it will be, what will it be? No. I think I didn't make a mistake. Let me see. I think I did make a mistake. Let's take H of X. Let's see what we can say about it. The tricky part is that so I'm claiming that we can define H of X to be S1 of X. Seems a very strong claim now. It has to be that. That's what I'm claiming. Now, why is this a very wild claim? Because S1 of X is some random element of this set. So it's a number that's less or equal to 1. How do I know that it will fall in this set? So after all, first we're proving. Okay, so here the proof of existence and uniqueness is not completely parallel. So let's, like before, let's first prove uniqueness very quickly, and then we'll prove existence. H of X, after we compose H with T1, this must equal S1 of X, right? Because of the commutativity of this triangle. Yeah. But of course, what is T1 H of X? Well, T1 maps every number to itself. T1 is just inclusion of this minus infinity 0 interval in this interval. So it is just H of X. So we will get that H of X must equal S1 of X. So that proves uniqueness. But now the existence is the one that's tricky. So how do we know that defining h of x this way is allowed? How do we know that S1 of x will indeed be an element of the set? Because as far as we know from here, S1 of x is just a number that's less or equal to 1. Any ideas? How can we establish that S1 of x must actually be less or equal to 0? Any ideas?
Well, it can't be positive because for any positive number, we can find some n such that 1 over n will be smaller than that positive number. So like, it's an issue here.
Sorry, I was interrupted on my side, Alexandra. Can you please repeat the last part of your sentence?
So the issue here is that for any positive number, we can find a integer n such that 1 over n is smaller than that positive number.
Yes. And so what? No, why do you say that? Because remember, this was a random cone, right? This S was a random cone. So
Yeah.
I picked a random element x here. And now I'm applying this map S1 to it. And all I know, it seems, is that S1 of x is an element here. How can I guarantee that it must be? So for instance, it could have been 3 over 4. How do I know that S1 of x cannot be 3 over 4? We need to remind ourselves the definition of a cone, what a cone is. In a cone, as we said, these triangles commute, each of them. So for any I for any I1 and onwards, we know that because we have a cone, we know that we have Si plus 1 map composed with, let's call these maps something, let's call these E1, E2, E3, and so on. Composed with EI must equal SI. This is because since S is a cone. But of course, EI doesn't change the number. EI is just an inclusion mapping. That's how we selected it. So each of these are inclusion maps. So overall we get that Si plus 1 of any x must always equal Si of that x. But this is for every I. So S1 of x will equal S2 of x, will equal S3 of x, will equal S4 of x, and so on. So here, when we randomly map this x by S1, here, because S1 is a composite of S2 and this inclusion, we can be sure that X1 falls in here, actually. Sorry, S of X1, because it must come from here, right? So S of x1 must be in this interval, but then because of this same reason, it must be here, and so on. So it must be in all of these. So S of x is an element of minus infinity 1 over n for every n. In other words, S1 of x is less or equal to 1 over n for every n. And that brings us to the argument that you were making, right? If S1 of x is less than every 1 over n, then it has to be less or equal, and it has to be less or equal to 0. Because as soon as it's slightly bigger than 0, we will find an n for which will no longer be less or equal to 1 over n. And so once we know that the values of h, the values of S1 lie entirely inside T, and we define h by this simple formula that h of x must be S1 of x, and the rest is then easy. So we just have to now confirm that going that way, now that we have a map, and randomly this way makes this corresponding triangle commute, right? But going down here is not changing anything because it's again the inclusion map, whereas this one is this corresponding SI, and if this behaves like S1, then we already know that S1 of x is always equal to any of the other S's. Does that make sense, or was it too fast at the end?
The original goal was to show that what is the terminal object, T or S?
T.
T. Okay.
Mm-hmm. So we proposed that it must be this, and then we took any S and confirmed that if H is to exist, H of x must equal S1 of x, so it's unique, because picking a fixed S means fixing S1 as well. So then for that S, H is unique. And then it does exist because it turns out that the values of S1 lie not only in here, but lie in all of these because of commutativity of these triangles. And if they lie in all of these, then their values must lie in this as well. In fact, this is the intersection. The more abstract version of this is that the limit of such a diagram would be the intersection of these sets, of the ones downstairs. Okay, so how is this similar to the product of two objects? How is this notion of limit similar to the product of objects? If we look again at product of a family of objects, we had, let's say we have 3 objects in the family. Product is what? Product P is an object P together with these projection maps, such that for any other object P prime together with the projection maps, we have a unique H here, right? That makes each of these, this triangle commute, that triangle commute, and this one commute. And this could have been an infinite amount of infinite family as well, right? So again, it's a cone versus a cone, right? So product is a cone, this time over a discrete diagram. Our starting point is just a sequence of objects that are not connected with arrows anymore. And we're looking for the universal cone, so the terminal cone. So if I have any other cone, then there must be unique morphism. And the limit, the way we looked at this example we looked before, is one where we had morphisms between our sequence of objects. So here we had objects without morphisms between them. Now we have morphisms between every consecutive pair. Otherwise, the rest it remains the same. But now, because we have morphisms downstairs, we want our cones to interact with them somehow. In this case, a cone didn't have to do anything because there was nothing to do. There were no morphisms downstairs. But now there are morphisms downstairs, and so we want these triangles to commute. But then the property is similar. So if I have another such cone, then there must be unique morphisms between them, where uniqueness is under the constraint that each of these triangles that are formed at every node are commutative, just like before we had these triangles commutative. So these two examples suggest what should be a general notion of a limit. So downstairs, we can have any fixed diagram. And what is a diagram? Well, a diagram consists of, first of all, a graph of objects and morphisms between them. And then each of those objects are labeled. And you can have repeating labels as well. Like in a product, we could have considered these all of these objects to be the same object. We'll be multiplying this object with itself then. It's not just the same as multiplying it once, because, for instance, you can have R cross R cross R. It's a three-dimensional vector space, which is different from just R cross R, which would be a two-dimensional space, right? So when you iteratively add things to itself, you do get something else than just itself. 1 plus 1 is 2. It is not equal to 1. So we can have repetitions among these nodes, but we still want to display them separately on the diagram so that we know that there is a repetition. So each of them have some labels. So this could be xi, this could be xj, and there are some morphisms between them, f, there could be 2 of them, g, r, and so on. So this is our fixed diagram. The diagram is always fixed. Like here, in the definition of product, we had a fixed underlying discrete diagram. In the definition of the limit of that we considered before, the special case, we had a fixed diagram as well. So we'll have a fixed diagram. Then we define a cone over it to be as an object together with one morphism for every node of the diagram. So just like the nodes are indexed by these numbers, by these values I and j, and not by, so here, the I and j can be different while xi and xj are the same, okay? It's the same way, these two morphisms that will be going into the ith node and jth node, let's call them pi I and pi j. When I and j are different, they will usually be different, even if these objects happen to be the same. It's like projecting from R cross R to R on the x-axis or y-axis are two different maps, even though we're projecting them to the same place. So this will be maybe, if this is xk, this projection will be pi k. So we've got all of these, one for every node. And we require that every time there is a triangle formed, like this one, that it commutes. So that's the definition of a cone. Now, a limit will be a terminal cone. But now first I need to define what is a morphism between cones. So if I have another cone, so this is, let's say, cone L, and let's say I've got another cone C, then it will have also these corresponding, maybe I will use a different color for that. CI, CJ, CK, and so on. So it has all these other morphisms, one for each node. So there are many of them, right? So another cone there. A morphism of cones is, let me use an orange map, is a morphism from C to L in my category. So all of this is happening in a single category. It's a morphism from C to L such that for every node, I'll pick a random node. Let's say we pick a jth node. For every node, the corresponding triangle commutes. So this triangle must commute. So going this way and then projecting by pi j must equal Cj. So that's a morphism of cones. And then we take the terminal or a-terminal cone, and that's called a limit. So a limit of a diagram in a category is a terminal cone over the diagram. The dual notion is the notion of a co-limit, and we will now conclude with an example of it. Dually, a co-limit of a diagram is an initial co-cone over that diagram. And let's now go back to the torus and see how we can actually represent that universal property as a colimit. So first we need to set up the diagram, then we will set up cones over it, and then torus will be universal one. So our diagram will have two spaces. One will be the rectangular piece. Remember, it had these two yellow parts that will stick to each other and two red parts. So this is one object. So we are in the category of topological spaces here. So objects are spaces and morphisms of continuous maps between them. Once again, if you don't know what they are, just think of them as, you can also think of them as sets. The level of intuition, it's fine. You can think of this set of points on the rectangular piece of paper or any other material. And then the other space is the red line and the yellow line. We take disjoint union of these two spaces. So these two lines are now separate. Is that what I want to do? Yeah, I think that's sufficient for what I want to do. So there are these two objects. So this space is one object, this is the other one. I'm setting up my diagram. Now I need two morphisms, U and V. So my diagram will have two objects and two morphisms, two parallel morphisms between them. The U morphism will match this yellow bit to the top part of the rectangle. So that's what U does. Let me actually use different colors for U and V. U will be blue and V will be purple. So U will match this with that. And it will match this red one with this. So it will be mapping these things. Whereas V will match the same yellow part to the bottom of the rectangle, and the red one, it will match to the right side. And now I'm going to be considering cones over this, co-cones over this diagram. So what does a co-cone over this diagram look like? It's some topological space S with two continuous maps, Let's call it iota 1 and iota 2. What do we know about them? We know that these triangles commute, right? One for every morphism here. So we will have this triangle that commutes, and we'll also have this triangle that commutes. So we'll have that iota 1 composed with u, sorry, the other way around. Iota 2 composed with u equals iota 1, and iota 2 also composed with v equals iota 1. And the purpose of this really is to be able to say that iota 2 composed with u must equal iota 2 composed with v, which is exactly what we get as a consequence of these two equalities, because on the right-hand side we've got the same thing, right? So these are the Kohn conditions. But what is this force? This forces a random point that was on the yellow line, which by the u map was mapping to the top bit, and by the v map was mapping to the bottom bit, right? After being mapped by iota 2, they must map to the same place in S. That's exactly the condition we had on this random thing we got out of the rectangle, where we were inserting the rectangle, folding the rectangle into some space. And so the initial object among such things, as we already know, is the torus. So our torus, with this map being the way we build the torus out of the rectangle, and this map just being the composite of that with the u and the v. So it's the way we indicated the red trace of where things got glued together, and the yellow trace of where things got glued together. So these are the maps. That will be also a co-cone, and the property we established earlier will be saying that this is actually initial co-cone among all co-cones. And in fact, we can represent every time we're doing some kind of quotient procedure, somehow going back to Alexander's remark, every time we're doing a quotient procedure, we can represent quotient procedure as a colimit. So many universal properties turn out to be colimit properties. Many of them turn out to be limit properties. And we then have the following scheme of concepts that we've built. So we had product, we had sum, which was dual to product. Even more primitive, we have terminal object, an initial object. And of course, product was more general than terminal object. Then something even more general than product is limit. And on this side, we have colimit. And something even more general is a universal property. So, but of course, that was being initial in some category. And so even more general is being initial. And we have the cycle of concepts, right? Being initial is a special case of sum. Sum is a special case of colimit. Colimit is a special case of universal property. There's a special case of being initial. But the reason why it cycles is because here we're taking initial in a different category, not the same one that we have here. And so this layer is very important, and it's a direct extension of the arithmetic layer. So we can call this layer some kind of generalized arithmetic. We can call this layer some kind of generalized analysis. But this layer is really where category theory lives. So whereas things from these layers kind of look similar to things we've seen before in mathematics, things from this layer is what makes I mean, if all universal properties were limits and colimits, then probably the subject of category theory wouldn't exist. That's what I'm trying to say. So there are many other universal properties also that are not necessarily limits or colimits. What is significant about these three layers is that all of them are inside a fixed category, whereas when we go to universal properties, we're now changing our categories. We can have, like with complex numbers, what we had, it's what is interplay between reals and another field. So, and then a fixed element of the field. And with tensor products, we also had bilinear maps. So we were not confining ourselves inside a fixed category, whereas limits and colimits do confine ourselves there. Right, so this is the end of today's lecture.
Thanks a lot. That was really interesting.
Thank you.
Goodbye.
Goodbye.
Thank you.
Brilliant lecture as always, Zurab. I guess today I might have to leave early, but yeah, I think.
Thank you, Batista. See you soon.
So we'll talk via email if there's anything
Yes.
that comes up. All right.
Yes.
Have a nice day.
Thank you, you too. Bye.
Bye.
Thank you, Zurab.
Thank you. Thank you too.